Okay, let's dive in. If you're anywhere near high precision manufacturing, you definitely know the struggle. It's not just the cost of materials, though that's huge. It's seeing profits get eaten up by wasted stock, especially the expensive stuff, or fighting with these incredibly intricate designs, trying to hit tolerances, long setup times, secondary ops. It all just slows things down. So today, our deep dive is looking at a really fascinating bit of engineering that tackles this head on, the Swiss-type lathe. We're digging into insights from Swiss lathe, precision, efficiency, and material savings, kind of cutting through the jargon to see why these machines are such a game changer. Right? Our mission here is to really get under the hood. How do these lathes pull off incredible material savings? How do they guarantee flawless concentricity and perfect perpendicularity? Basically, how do they hit this amazing accuracy and efficiency that often leaves traditional lathes behind? We want to unpack the how and the why. So let's start with that big one, material waste. I mean, it feels like every spare inch of bar stock you waste, especially that pricey titanium or medical steel, is just money down the drain. It's a real strategic headache. How do these machines actually fight that?
Well, the core idea is actually pretty clever. It revolves around two key components, the sliding headstock and the guide bushing.
Okay.
So, unlike a traditional lathe where the tool moves along the part, here the part itself, the bar stock, slides through this guide bushing.
Yeah.
And that bushing gives it super rigid support, like right at the point where the cutting happens.
Ah, okay. So it's supported right there.
Exactly, which means you can machine almost the entire part from the bar, leaving only a very small remnant, maybe an inch or so.
Yeah.
And because it's all done in one setup, you completely avoid the waste you get from clamping and reclamping on other machines.
That makes sense. Less handling, less waste.
And there's more. Because of that rock-solid support from the guide bushing, right at the cutting edge,
Yeah.
you can take much deeper cuts, more aggressive cuts in a single pass. Think about a standard lathe, push too hard on a long, thin part, and it'll just bend or vibrate, right?
Right. You'd have to take multiple shallow passes.
Exactly. But here, that support stops the deflection. So one deeper pass instead of several shallow ones. That means way less wasted movement and, crucially, much faster cycle times. It's a fundamentally different approach.
Okay, that efficiency angle is interesting. So this ties into that idea of one-and-done machining you sometimes hear about.
It does, yeah. That's pretty much the goal.
Is that truly realistic for really complex parts, though? Or are there still cases where you'd need multiple setups?
That's a fair question. Look, one and done is the ideal, and honestly, it's achievable for a surprisingly wide range of complex geometries. A big part of that is the machine's ability to do everything turning, milling, drilling, all in the same cycle.
All at once?
Well, sequentially, but without moving the part to another machine. And the sub-spindle is key here.
Ah, the sub-spindle.
Right. So after the front end is done, the sub-spindle can grab the part, cut it off, and then work on the back end, all in one continuous process. This completely gets rid of needing extra material just to reclamp the part later. You're using almost the entire bar. It's about optimizing the whole flow.
Okay, so the numbers must be pretty compelling then.
Oh, absolutely. When you combine all this, the single setup, the deeper cuts, the sub-spindle back working, you can push raw material utilization up towards like 98% in some cases.
Wow, 98%.
Yeah, and that can translate to overall material savings of maybe up to 30% compared to older methods. So for you, the listener, if you're using those really expensive alloys, that's not just saving money. It could make some complex designs economically feasible for the first time.
Opens up possibilities.
Definitely. The waste reduction comes from that single setup, deeper single passes, and using the sub-spindle effectively.
Okay, saving material is huge. But what about another big precision headache? Concentricity. Features on a shaft not lining up perfectly, that causes vibration, poor performance, maybe even failure. And one tiny error can scrap a whole batch. How do Swiss types guarantee things run true?
Right. Concentricity is absolutely fundamental, especially for anything that spins or fits together precisely. There are really two main things working together here. First, the main spindle itself is built to incredibly high precision standards. It's designed to spin perfectly true, minimal run out.
Okay, starts with a good foundation.
Exactly. But then you add the guide bushing again. Remember how it supports the workpiece right at the cut?
Yeah.
Well, that support also prevents the workpiece from wobbling or having any kind of run out as it spins and feeds forward. It keeps everything centered right where the tool is working.
So the bushing is doing double duty support and centering.
Precisely. But for really complex parts, where you have features on both ends that need to be perfectly aligned, the real magic, you could say, is the sub-spindle.
Okay, how does that guarantee the alignment?
Well, after the front of the part is machined by the main spindle, the sub-spindle, which is perfectly aligned with the main spindle, comes in. It moves forward and clamps onto the finished part before it's actually cut off from the bar stock.
Ah, I see. Well, it's still held.
Exactly. Then it cuts off and pulls the part away for any back working operations. Since the transfer happened while it was held in alignment by both spindles.
The features on both ends have to be concentric.
Guaranteed. It's a very clever transfer mechanism that preserves that perfect alignment. It's a huge factor for complex component integrity.
That is clever. Really rethinking the process flow. Okay, so that handles rotational accuracy. What about drilling straight holes? Especially tiny ones. We've all seen a small drill bit just walk off center, right? You end up with a crooked hole, useless part. How do they nail perfect perpendicularity?
Yeah, drill walking is a classic problem, particularly with small diameters or deep holes. Swiss machines tackle this with a couple things. Often they use what's called live tooling.
Live tooling.
Yeah, instead of just a static drill held in a turret, you can have rotating tools. Specifically, for drilling perfect holes, they might use high-frequency milling heads.
Milling heads for drilling.
Sort of. Think of them as miniature, very high-speed spindles. Instead of just pushing a drill bit, they sort of mill the hole at very high RPMs. This creates a cleaner, much more precise hole with less tendency to wander off course. And of course, using high-quality drills with the right geometry is also key.
Okay, so specialized tools help, but what about the machine itself?
Right, the tooling is only part of it. Controlling the process is critical. The inherent rigidity of the machine structure helps a lot. Plus, that guide bushing support, again, it prevents the workpiece itself from shifting or vibrating under the force of the drill.
Keeps everything stable.
Exactly. And then the machine has incredibly precise control over the feed rate, how fast the drill advances into the material. Finding that optimal feed rate is crucial. Too fast, it might deflect. Too slow, it might rub or wander. The machine control ensures it goes in straight and stays straight. It's about minimizing every possible source of error.
So you put all this together, the material savings, the concentricity, the perpendicularity. What does it mean for the bottom line in terms of overall accuracy and efficiency compared to maybe traditional lathes that can be, let's face it, a bit slow and might struggle with really tight tolerances on tricky parts? Where does the Swiss machine really pull ahead?
Well, connecting it all, it represents a significant leap in capability. We're talking about a level of accuracy that's kind of mind-blowing. These machines can consistently hold tolerances down to 0.0001 millimeters.
0.001 millimeter, that's tiny.
It's incredibly small. About 170th the width of a human hair. And that's achievable mainly because that guide bushing eliminates the vibration and deflection right at the cutting point. For industries making things like, say, spinal implants, microsensors for aerospace, complex watch components, that level of precision isn't just nice to have, it's absolutely mandatory.
Okay, accuracy is top tier. What about speed?
Yeah.
Efficiency.
Huge gains there, too. A big factor is the multi-axis capability. A typical Swiss machine might have, 7, 9, maybe even up to 13 axes working together.
Compared to what, 2 to 5 on a standard lathe?
Exactly. And having all those axes means multiple tools can cut the part simultaneously. It's like a carefully choreographed dance. So you might have a turning tool shaping the outside diameter, while at the same time a live tool is drilling a cross hole or milling a flat.
So operations overlap.
Precisely. This overlapping, which is all planned out using sophisticated CAM software, dramatically cuts down the cycle time for each part.
Right.
And then you add an automatic bar feeder, which can feed new stock into the machine continuously.
Ah, so it can run unattended.
For hours, yeah. Perfect for high-volume production runs. Lights out manufacturing, essentially.
That combination of speed and automation sounds powerful. But what about the cost? Are these machines incredibly expensive? Is that a barrier for, say, smaller shops?
That's a really important practical point. Yes, the initial investment for a high-spec Swiss-type lathe is definitely higher than for a simpler traditional lathe. It's a significant capital expense.
Right.
But you need to look at the return on investment, especially if you're making complex parts in volume or parts from expensive materials. When you factor in the material savings, the elimination of secondary operations, the drastically faster cycle times, and the ability to run unattended, the cost per part often drops significantly.
So the ROI can be quite fast.
For the right kind of work, absolutely. For smaller manufacturers aiming for those high-precision, high-value niches, investing in a Swiss machine can actually be what gives them a competitive edge. It lets them take on jobs they couldn't handle before. It is a shift towards more capital-intensive production, but it unlocks a higher level of capability and profitability.
Okay, that makes sense. So, wrapping things up then, Swiss-type lathes bring, well, a whole package.
Hmm.
Massive material savings, that guaranteed concentricity and perpendicularity, and just phenomenal accuracy and speed. It really seems clear why they're the go-to for complex, high-precision parts where profitability depends on getting it right first time, every time. It really does seem to open up new possibilities.
Absolutely. And if you step back and look at the bigger picture, it's a fantastic example of how specialized, clever engineering can solve fundamental problems and really push an entire industry forward. Allows for innovation in places you wouldn't expect.
So here's something to think about for you listening. We've seen how this support right at the cutting point philosophy totally transforms precision machining. Where else could that core idea be applied? What other industries or even everyday products face challenges where tiny errors cause big problems and where supporting the work exactly where the action happens could be the key? Think about that. Where could this kind of thinking unlock the next impossible challenge?